Just a second. See this. Just so here. Okay. Example of applying Rodriguez formula. Let's see, this one is just a second. Connect. Table. Example of applying Rodriguez formula. Okay. Suppose we want to rotate vector R equal to, let's say it's 3, 4 minus 2. By 30 degrees around axis through the origin with unit vector 1/√3, 1, 1, 1. So it's a axis that is equally inclined to all three axes, And the R is some vector there. 3, 4, and -2. So this is the R. We want to rotate it around this N by the angle 30 degrees. Want to find the matrix. So Find matrix R. Okay. The matrix is given by the following expression. It's an identity matrix, three-dimensional, times cosine of the angle by phi cosine phi plus the n tilde, we'll explain what it is, times sine phi plus the vector n as it is multiplied by the n transpose multiplied by 1 minus cosine phi. This angle is counterclockwise, right? Okay. Let's figure out all these pieces. I3 equals to, well, it's easy, it's identity matrix. The n tilde, that's the one that is equivalent to rotation. Remember, the n tilde is coming n tilde times vector r times vector v, for example, right? Make it r, right? N tilde times r, it's a matrix, right? Okay. It's the same as n cross product with r. So the n tilde is equal to 0 minus n2, sorry, minus n3, n2, and we have n3, 0, minus n1, and here it's going to be minus n2, n1, 0. So that's going to be, all of them have a 1 over root 3. Remember, the n is this one. So the third component is, let's just, pardon me. It's going to be minus 1, 1, 1, 0, minus 1, minus 1, 1, 0. That is the n tilde, right? Okay. Now then, the n vector times n transpose, which is a row vector, will be n1, n2, n3, multiplied by n1, n2, n3. And that will be a matrix which has component n1 squared, n1, n2, n1, n3, n2, n1, n2 squared, n2, n3. Now there's going to be the n3, n1, n3, n2, and n1 squared, n3 squared. And since all components are the same, they're all equal to 1 over root 3, 1, it's going to be, each of them will have a 1/3. So it's going to be a 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, and 1/3, right? All right. That's this one. Or we can write down as 1/3, and that's going to be a 1, 1, 1, 1, 1, 1, 1, 1, 1. That's all we need, and now we'll do the computation. And that's going to be the following. So the R rotation matrix around the N by angle phi Rodriguez matrix will be 1, 1, 1 cos of pi over 6 plus and tilde is this one. 1/3 0 minus 1 1 1 0. This will be minus 1, and that's going to be minus 1 1 0 times sine pi over 6. That's √3/2, and that's 1/2. And plus the last one, which is going to be 1/3 plus 1/3, and that's going to be 1 1 1 1 1 1 1 1 1 times 1 minus cos of pi over 6. I will do computation in Scilab. It's easier for me. Let me open the Scilab there. I don't have MATLAB on this computer. Let's see. See where it is. Okay. Let me just check something. Okay, let me first stop sharing and share the Scilab with you. So I need to share the following. Let's see. What is the I of 3? I suspect this is identity matrix. How about I of 3/3? Yes, okay, that's the identity matrix. All right. The other ones will enter as it goes. All right. So we'll now start out with n equals to 1 over square root of 3 times 1 1 1 prime. So it's a column vector. All right. Okay. So now we can proceed with the formula. Let me just double check if the angle by default is in radians, right? Okay. Percent pi. All right. Sine of percent pi over 6. Let's see if it's going to be in radians or in degrees. Yeah, that's fine. All right. So good. So the R rotation matrix, capital, equals to the I 3 by 3, sorry, yeah, 3 by 3, multiplied by cosine of pi over 6, right? Plus n tilde, and that is going to be 0 minus 1, 1, 1, 0 minus 1. Zero minus 1, 1, comma, 1, 0. Is it minus 1, minus 1, comma, and we'll have the minus 1, 1, and 0. Multiply by, okay, just a second. Zero multiplied by, I believe, sine of pi over 6. Okay. And plus the n vector multiplied by n transpose and multiplied by 1 minus cos pi over 6. The one place where I missed the percentage sign is here. Okay. 6. Well, let me see. Syntax error expected. Okay. I this plus sine pi over 6 n. Okay. One extra parenthesis, right? Okay. We need one more parenthesis. That's cosine. Okay, R equals to. That's the rotation matrix. Okay. So let me then copy this thing to OneNote. Okay. Three, 4, and -2. So go back there. And we have mu of the R original vector was equal to 3, 4, -2 prime, so it's a column vector. And the new R, after we rotated it, is equal to capital R times R. Okay. Copying it there. That's it, right? Okay, now we stop share on the Scilab and the share screen with this. Okay. Any questions about this? Right, let's go to the next page. Matrix. Formulation. Of angular velocity. Again, this is a material that you might need at in your robotics class and so forth, right? Okay. Let Q be rotation matrix. This is a function of t. Okay. So at any next moment, the r of t equals to the q of t times multiplied by the r at 0. Okay. You apply rotation q, which is, for example, like one of the Rodriguez matrix, right? To r of 0, and you get the r at position t, right? Time t, right? Okay. From here, for example, r of 0 equals to q inverse times r of t. Now, velocity, that's in rotational motion. Now, velocity, of course, is dr over dt. And differentiate this one is going to be q dot times r of 0. Now, this can be written down as q dot, and instead of r of 0, we'll write down the q inverse of r of t. So we can see, but we recall that velocity in rotational motion equals to omega cross product with r. And therefore, the q dot, q inverse, is that magic omega tilde matrix. It's the matrix of angular velocity. Just a second, something. Okay. Which is equal to, as we discussed the other time, 0 minus omega 3, omega 2, omega 3, 0 minus omega 1, and it's going to be minus omega 2, omega 1, and 0. Okay, that's a little bit of an excursus in the rotation versus angular velocity. Okay. At some point, we'll have vectors expanded in a rotating reference frame. You will see why. It has to do with inertia matrix. It is constant in body axis, but varying in space axis, in space inertial axis. This body axis rotate relative to inertial frame. Okay, so we'll need that. Suppose B is a vector and it's equal to summation of BI of t times EI of t. And these are rotating reference frame. That's any arbitrary vector. Could be velocity, could be angular momentum, etc. Right? What's going to be its derivative? dB over dt will be equal to, on the one hand, derivative of this is going to be summation of BI dot times EI plus summation of BI times EI dot. Now we know that EI dot equals to omega cross product with EI. That's the angular velocity of rotating frame. Therefore, the dB over dt equals to, this one will be dB over dt in frame R. As frame R is E1, E2, 3, plus summation of BI omega cross product with EI, which will become dB over dt in R plus omega cross product with B. And that's the formula. Oops. Formula to find the derivative of a vector in rotating frame. It's going to be derivative of the vector in the frame plus omega of the frame R relative to inertia, relative to A. This is inertial frame. Cross product with B. Newton-Euler equations. For a rigid body. In rotation. Well, first one is summation of the forces equals to the mass of the body times dV over dt. And that we'll write down as mass times dV over dt in the rotating frame plus the m omega of the frame cross product with B. So if we write down the equation in rotating frame, it's going to be like this. We'll have a term where this is in the rotating frame. Rate in rotating frame. Okay. Now, the moment. The angular momentum, as we developed sometime in the past, about point O, that is fixed point, HO equals to the tensor of inertia I about O times vector omega. Same with center of mass. The H about C equals to the I about C times omega. You guys remember what the inertia matrix is? Anybody? You guys alive there?
Yeah.
The I matrix is, for example, O will be IOXX minus IOXY minus IOXZ minus IOXY IOYY minus IOYZ minus IOXZ minus IOYZ IOZZ. Now, these moments of inertia will change if the body rotates. That's your X, Y, and Z are rotating coordinates frame. So in other words, they are body axes. Okay. Now the Newton-Euler says that the sum of the moments about point O equals to the rate of change of angular momentum about point O. We developed it in the past. Which is going to be dO dt of I matrix times omega vector. And this we can write down in the following way. It's going to be the I matrix times d omega over dt. That's in the rotating frame, plus omega is the body's angular velocity. And plus the capital omega cross product with the angular momentum, which is I matrix times omega. This is the angular velocity of the reference frame. Special case is when this one is the same as the body, right? So in this case, the MO equals to I matrix times omega dot plus omega cross product with the I multiplied by omega. In principal axis, the I is equal to I1, I2, and I3. So we can expand this thing and we get the following, that M sub O equals to I1, I2, I3 times omega 1 dot, omega 2 dot, and omega 3 dot, plus the omega, we'll write it down in this form, cross product. It's going to be omega 1, omega 2, omega 3. Sorry. Let's do the other one. IJK, omega 1, omega 2, omega 3. And this will be H1, H2, H3. These are components of the angular momentum. So, for example, the MOX equals to I1 omega 1 dot plus this one, omega 2 H3 minus omega 3 H2. Now that will be equal to I1 omega 1 dot plus omega 2, and H is this guy. We wrote it down somewhere. Let's write it down. Then the H vector equals to I1, I2, I3 times omega 1, omega 2, omega 3. And that will give I1 omega 1, I2 omega 2, and I3 omega 3. So the H3 will be I3 omega 3 minus omega 3. H2 is I2 omega 2. With my notes, that's what I got. That's what I get. So we write down again that MOX equals to I1 omega, or we can say 1. That's just a second. Omega 1 dot plus I3 omega 2. Well, sorry. We can factor out plus omega 2 omega 3 times I3 minus I2. And then we'll do the by circular transposition, we have MO2 equals to I2 omega 2 dot plus omega 1 omega 3 times I2 minus sorry, I1 minus I3. Just a second. It can be 1, 3, 2. So 1, 3, 2. Then this one is 2, 1, 3. And MO3 equals to I3 omega 3 dot plus omega 1 omega 2. 3 will be 2, 1. I2 minus I1. These three equations combined with the plus the translational equation that we wrote before, those make Euler-Newton equations for rigid body. Just a second. Special case. When the body is body of rotation, about axis 1. Then I2 equals to I3, and we set it equal to I naught. I1 is different one. So the result will have that the rotational part is MO1 equals to I1 omega 1 dot. And these two moments are equal. I3 equals to I2. So therefore, that's it, right? Okay, the first equation. MO2 equals to I2 omega 2 dot plus the omega 1 omega 3. I1 minus I naught. MO3 equals to I3 omega 3 dot plus omega 1 omega 2 I2 minus I1 I0 minus I1. Okay. Now we'll do a little bit more about the things that I need to. There's some other items that are covered in intermediate dynamics, but are not covered here. And we will cover them. Something else, right? Okay. Combining angular velocities. Suppose this is a rigid body. That's an axis of rotation. And we have another axis right here. This is, let's call this axis N1. This is N0. Suppose the body is rotating with angular velocity omega relative to N1. But the N1 also is rotating with angular velocity omega of N1 relative to N0. Okay. Then the angular velocity and these angular velocities crossing each other. Then in that case, the resultant angular velocity equals to omega relative to N1 plus omega N1 relative to N. That's the law of combining the angular velocities, right? Okay. Okay, well, I have an example. I'll try to draw it up. That's the axis, little x, which is the same as x, and that's the fixed axis. It doesn't rotate, right? Now this cylinder let me make it a little bit shorter. Okay. This axis is piercing through the cylinder. The cylinder has axis that is inclined at an oops. This angle is gamma, and gamma dot is also here. And at the end of this axis, there is a wheel. Okay. With center C. This axis we call Z. Okay. It is rotating, as you can see by the angle gamma. This point is O. This is A. And the cylinder is rotating with angular velocity omega naught. This is the y-axis with J. Okay. And that's the X. This is Y. The Z should go the other way around. Let me just make it like this. That's the Z-axis is pointing this way, right? Okay. Oh, no, just a second. Let me think. No, it's correct. That was correct. Okay, so X, rotation from X to Y, and this is the Z-axis, right? Okay. So what's given is omega naught equals to 120 RPM. Well, you convert it to the radians. That means you divide it by each rotation is 2 pi. And to get to the seconds is 60. All right. So there's going to be a 4 pi radian per second. The gamma dot equals to 3 pi radian per second. The gamma at the moment, gamma equals to 30 degrees, but that changes, right? Okay. In rotating frame, X, Y, Z, find the alpha of the disk, that's disk, the velocity of point A, well, I didn't mark it correctly. The A is there on the disk. That's the A. Disk. VA. And acceleration of point A. Okay. Omega disk resultant equals to omega disk relative to the motor. The motor is the one that's rotating, plus the omega of the motor. This is the motor. The cylinder is the motor. The omega disk is omega naught times K. The mega motor is minus gamma dot times I. You can see that the gamma, this rotation occurs around this axis. That's why it's gamma. It's gamma. So there's going to be 4 pi times K plus minus 3 pi times I. alpha of the disk equals to d omega of the disk over dt. That's going to be two pieces. First, this is constant, so it's going to be 0 times k plus 4 pi times k dot. This one will be minus 0 times I plus minus 3 pi times I dot. And that will be 4 pi. This will be omega motor cross product with k. Because this is omega of the disk relative to motor, right? Okay. Times k plus minus 3 pi times I dot. And I dot is 0. You can see that axis is fixed. The result will be 4 pi times omega motor cross product with k. And that will be 4 pi times minus 3 pi I cross product with k. Now the I, j, and k will be the I dot k will be minus j. That's going to be the 12 pi squared times j. That's the alpha of the disk. Angular velocity of the disk. Now the linear parameters. VA equals to V naught, V of the point O, plus omega resultant cross product with OA. Now OA equals to OC plus CA. Now I didn't provide all the information. Let me write it down. I think it was written here, but I didn't say. Okay, I forgot to write down that here that OC this is C, this is O. So OC equals to 10 inches, all right? And the radius of the disk equals to AC, and that's 5 inches. So going back to this one. OC, that's going to be 10K plus 5J. Okay. So the result is that the VA equals to resultant angular velocity 4 pi K minus 3 pi I. Cross product was 10K plus 5J. There's going to be 40 pi K cross K, which is of course 0, minus 30 pi I cross K. I cross K will be minus J, plus 20 pi That's 4 pi this of k cross j. Which is k cross j with minus I. And minus 15 pi times I cross j, and that's a k. It's going to be 30 pi plus 30 pi j minus 20 pi I and minus 15 pi k. That's going to be the velocity of point A. Acceleration of point A equals to acceleration of point O plus acceleration of A relative to O. The acceleration of point O is 0. And that one is alpha resultant cross product with OA plus that's when you differentiate first piece. But when then you add this one, omega res, resultant cross product with omega resultant cross product with OA. Okay. That happens when you differentiate this one, right? Okay. You have D, you have the alpha AA equals to V naught dot, which is of course 0. Oops. Plus alpha resultant cross OA plus omega resultant cross omega resultant cross OA. That's the equation that we're going to use now, and V naught equals to 0. Okay. And this will be 12 pi squared j. That's the alpha resultant in the moving coordinate frame. Cross product with 10k plus 5j and plus 4 pi k minus 3 pi I. Cross product was 30 pi j minus 20 pi I minus 15 pi k. After everything is done, we'll have the following results. Minus 125 pi squared j minus 90 pi squared k. That's acceleration of A. This little bit of review of kinematics, 3D kinematics. Right. We have more example. Recall in 2D kinematics, we had ICV, instant center velocities. In 3D, kinematics, we have instant axis of rotation. All right. So example will be something like this. You have a plate, base, thick foundation, and you have an axle here that is on roll bearing, and it's rotating. And to this axis, we have attached a wheel. So as this is rotating, the wheel will also be rotating, right? Okay. This point will be moving this way, right? So therefore, the wheel will be rotating about this axis like this. That's axis. This radius r, okay? So what you notice is the wheel is moving with this point being this is point A, and we can say the velocity of A is 0 all the time. But the A is the point of contact. So once it moves a little bit, the A will be above, but the point of contact velocity is 0. So velocity here is 0. Okay. The other point whose velocity is 0 is right here. That's the O. Velocity of O is also 0. So we have these 2 points that are fixed. Therefore, the line connecting them, this one. Oh, let me just draw it better. This is the instant axis of rotation at the moment. Okay. As the wheel rotates, right there, right, about the axis, about the line O, OB, for example. From the point of view of the wheel, of view of observer on the wheel, the axis of rotation describes the axis of rotation. When you observe there, how do you see this thing moving? When you observe sitting on this one, when you're here, it's down there. When you're there, it's down here. So the result of this, it describes a cone. It describes what is called a body cone. That looks like this. So from the observer on the wheel, that's the cone that is described by the axis. Okay. When he is here, he sees this one down here, right? When he is here, he sees this one down there, right? Okay. When he is there, all right. But from the point of view of observer on the ground, but from the observer in the observer in inertial frame, means on the ground, the axis. So this axis of the observer on the ground just moves around like this, right? Around like this, okay? The axis describes what is called the space cone. That will be shown. So this is a space cone that is described. If you combine these two, this is the body cone. This is space cone. And they are tangent to each other on the axis, instant axis of rotation. Okay. So the body cone rolls on the space cone, right? Okay. Okay, good enough. And we'll talk more next time. Have you guys had this thing? Those of you who had intermediate dynamics?
No, Professor, we didn't have.
Okay, good. Good that I brought it up to you. All right. Have a nice day. See you on Wednesday.
Thank you, Professor.
See you. Thanks.